Welcome to Lecture 22, whose subject is heat transfer. It's kind of a redundant term because, as you learned in the previous lecture, heat means energy that is in transit, that is being transferred from one place to another because of a temperature difference. So heat transfer is kind of a redundant term, but it's widely used in physics and engineering to describe the processes whereby heat flows. So we want to ask here, how does heat flow? We've got a temperature difference, we've got a heat flow, but why? What process is carrying the energy? And this lecture is going to look at three important mechanisms of heat transfer and some applications both in technology, in simple things like building design, and in nature as well. So the first heat transfer mechanism, and in some ways the most familiar one, is conduction. Conduction is a process of heat transfer between objects that are in direct contact. So let's take a look. Here's a beaker sitting on a hot plate. The hot plate is hot. It's being heated by electrical energy that's warming up this top of the hot plate, and the beaker is in contact with the hot plate, so energy is moving directly by contact between the metal of the hot plate and the glass of the beaker and then into the water. What exactly is the details of that mechanism? The details are that the internal energy, the temperature of this hot plate is high. And as we'll see in another lecture or two, internal energy is a measure ultimately of molecular motion, molecular kinetic energy, molecules moving around, and when the temperature is higher, they're moving around faster. So the rapidly moving molecules in the hot plate are colliding with more slowly moving molecules in the walls of the beaker. And when a molecular transfer like that occurs, it tends to move energy preferentially from the hotter, that is, the faster moving molecules, to the slower moving ones. And then the molecules in the beaker transfer their energy further on. And that process of direct contact, materials in contact, is what transfers energy by conduction. Eventually, the energy gets to the inside wall of the beaker, where it's transferred by conduction to the water. And then another mechanism, which we'll discuss shortly, takes over. So heat transfer by conduction is a molecular process that requires two substances to be in direct contact, otherwise heat can't flow through them. We happen to be recording these lectures in January, so in here it's a nice comfortable temperature in the studio, but outdoors it's actually a little bit below freezing. And so the walls of this room are transferring heat through themselves to the outside because of the temperature difference between the inside and the outside, and we have to burn fuel or consume electricity or something else in order to make up for the energy being lost, largely through conduction through the walls. Let's take a more detailed look at how conduction actually occurs. So let's go over to our big monitor and do some mathematics of conduction. So to give you a simple picture of conduction, here's a slab of material of some sort. And I'm going to assume that one side of the material is at a high temperature, TH, and the other side is at a lower temperature, TC, the red for hot, the blue for cold. The slab has an area A, and it has a thickness delta X, and I've indicated by these wavy lines a heat flow, which I will designate H. So that's the conductive heat flow, because I'm talking about the process of heat conduction. It's measured in watts. It's the rate at which energy is being transferred. Rate of energy is power. So this is the power flowing through that particular area A of that slab of material. And what's that depend on? Well, clearly it depends on the area A. If I make the area A bigger, I've got more molecules to do that transferring, and so the heat transfer is going to be, say, make the area twice as great, there'll be twice as much heat being transferred. So the conductive heat flow will be proportional to the area. Certainly it will be proportional to the temperature difference. If I make the two temperatures the same, there's going to be no heat flow. The molecules are moving at the same average speed on both sides. But if one side is hotter than the other, then that energy transfer process that I described microscopically occurs, and a flow develops of heat, of energy, that is proportional to that temperature difference, delta T, T hot minus T cold. There's also a property of the material that helps determine how much heat flows through it, and that property is called the thermal conductivity. It's given the symbol K. It's how good a conductor of heat a substance is. If K is big, it's a good conductor of heat, and for a relatively small temperature difference, you get a large flow. If it's small, the material becomes a good insulator, and you get relatively little heat flow for a given temperature difference. And it's inversely proportional to, not surprisingly, the distance. The longer the distance the heat has to go through, the harder it's going to be for it to flow. So the thickness, delta X, also comes into this calculation of the heat flow. Put that all together, and you get that the heat flow is proportional to this thermal conductivity, the area, the temperature difference, and the thickness. This quantity, delta T divided by delta X, the rate of change of temperature with position, is called the temperature gradient, and it's positive in the direction that goes from lower to higher temperature, and so there's a minus sign here that tells you the heat flow is opposite the temperature gradient. In this case, the temperature is increasing to the left, and the heat flow is to the right, and that's what that minus sign means. So that's the mathematics of heat conduction. It's a relatively straightforward process. It depends on again, the thermal conductivity, the area in question, and the temperature gradient, or equivalently, the temperature difference, and with it, the thickness, the distance through which the flow has to go. Let's take a look at a simple table of some values of this thermal conductivity. Here are some thermal conductivities of typical material, air, aluminum, concrete, and so on. I'm not going to spend a lot of time on it, but you should notice that the two materials really stand out with having much greater thermal conductivity than other materials, and those are aluminum and copper. And if you think about it, those are also excellent conductors of electricity. And when we get to electricity, we'll understand a little bit more about the conduction mechanisms that allow these materials to carry electric current. They involve a lot of free electrons whizzing around in the material, and it's those same electrons that can carry heat, can transfer energy as heat. And so not surprisingly, the metals, aluminum and copper, the good electrical conductors, tend also to be good conductors of heat. Another interesting example here is fiberglass versus glass. Glass is actually a fairly good thermal conductor with a K of about almost 1 in SI units, but spun fiberglass, because it traps a lot of little air pockets in it, is actually a relatively good insulator, a poor conductor, as is, for example, styrofoam. Water is somewhere in between. Pine there, wood is a fairly decent insulator, but not great. So those are some examples of thermal conductivities that you might use to figure out what heat flows would occur through materials of particular thicknesses and areas. One way we express the process of heat conduction, particularly in building materials, and talking about building houses and building energy-efficient houses and so on, in the United States particularly, is with something called R value. Well, we have R value in other countries, but it's expressed in different units. In the U.S., it's in English units. And the R value measures the resistance to the flow of heat of a material. It's units. We almost never say it's units. We say this thing has R10 or this thing has R20. It does have units, but it's much easier to understand the inverse of the R value. So let's look at the R value. It's a measure of resistance to heat flow. The values of adjacent layers add, which is part of what makes it useful. So if I'm thinking about a house, I can think, well, I've got an R value associated with the sheetrock on the interior wall, and then an R value associated with the actual insulation in the wall cavities, and then maybe an R value associated with the plywood sheathing, and then an R value associated with shingles or whatever I've got on the outside of the house, and I can simply add them up to get a composite R value for the whole wall. That's why this is useful. Its units in the English system that we use in this country, in the United States, are feet squared times degrees Fahrenheit times hours per BTU. Wow, that's a mouthful. What's a BTU? It's a British thermal unit. It's a unit of energy. It happens to be the energy required to raise a pound of water by 1 degree Fahrenheit. More importantly, it's about 1,000 joules, about a kilojoule, 1054 joules. It's just another unit of energy. More meaningful is the inverse. It's called U. It's not conductivity, but it's a kind of thermal conductance. It's 1 over the R value, and its units are BTUs per hour, per square foot, per degree Fahrenheit. What does that mean? It means if I have a piece of insulating material, and here I've got a piece of styrofoam or polystyrene, extruded polystyrene insulation. It's 2 inches thick. This is the kind of stuff you'd use on the walls of a basement, for example. It's 2 inches thick, and it happens to have an R value of 10. What does that mean? It means if you take a square foot of this insulation, and so there's an actual square foot drawn there. If you take a square foot of that insulation, it will lose 1/10, the inverse of that number, of a BTU, of a British thermal unit. That's about 100 joules, because a BTU is about 1,000 joules. It will lose about a tenth. It will lose a tenth of a BTU every hour for every degree Fahrenheit of temperature difference between the hot side and the cold side of the styrofoam. So that's what R value means. And we can look at a table of R values of common materials. Concrete, for instance, is not a very good insulator. An 8-inch concrete wall has an R value of only 1.1, which is why we like to put that on the outside of a foundation wall. Makes that R value go up about tenfold. Fiberglass, 3.5 inch in standard 2x4 stud walls is about 11. 5.5 inch in standard 2x6 stud walls is about 19. You can see some other materials here, including windows. The best commercial windows have R values of up to 11, but they're extremely expensive. Typical good double-hung windows, 2, 3, 4, really fancy ones, 5, single-pane windows, less than 1. So you get an idea of the relative R values, the relative resistance to heat flows of different building materials. Let's take a look at an example where we use the R value. And for once, I'm stepping away from the SI system and using English units because that's what's used in the building industry in the United States. So heating a house. Here we've got a house, this particular house, and it's a really simplified house. It's 32 feet wide, 24 feet deep, 8 feet high. It's flat, it's rectangular, it has no windows, nothing like that. I'm ignoring heat loss through the floor because the ground tends to be warmer than the surrounding air. And I want to know when it's 70 degrees inside and 10 degrees Fahrenheit outside, how much oil, which you get about 100,000 BTUs when you burn a gallon of oil, how much oil does this use on a winter day when it's 70 degrees in and 10 degrees out? So we've got a temperature difference delta T of 60 degrees Fahrenheit. We've got a ceiling area of 24 times 760, 24 times 32, 768 square feet of R30 ceiling. The insulation is R30. That means we lose 1/30th of a BTU per hour per square foot per degree. So the ceiling heat loss rate is 1/30th of a BTU per hour per foot squared per degree Fahrenheit. Multiply it by 768 feet squared and multiply it by that 60-degree temperature difference. We lose about 1,500 BTUs every hour through the ceiling. The walls, we got 2 times this much plus this much, so that's 2 times 32 feet plus 24 feet times 8 feet. That's 896 square feet, about the same as the ceiling, a little bit more. On the other hand, that's only R12, so we lose 1/12th of a BTU per hour per square foot per degree Fahrenheit. So the wall heat loss rate is 1/12 times the 896 square feet times the 60 degrees. That's almost 4,500 BTUs per hour, much greater than the ceiling loss because we got much less insulation in the walls. So there's a lot more wall loss. There's a little bit more wall area, but not too much. Add those up, you got about 4,500 and 1,500. You get about 6,000. That's the total heat loss rate, about 6,000 BTUs every hour. There are 24 hours in a day. Multiply 24 by 6,000, you get 144,000. I'll call it 150,000. And if we compare that with oil, we see that this house uses 1.5 gallons per day. Now, that's a naive calculation. There's no windows. I left out an awful lot. But you can see how the idea goes. How, if you were a heating and contracting engineer, you would end up sizing a house or calculating how much insulation it needs or how big a furnace it needs or whatever. So that's R value, a measure of resistance to heat flow. Let's move on to another example of a heat flow mechanism. Let's talk about convection. Convection is what happens once the heat conducted from the hot plate into the beaker and reached the bottom of the glass. Then what happens is the water is warmed, the warm water expands, becomes less dense, and the warm water rises. And it carries with it the internal energy that is within it, and that rising of that internal energy constitutes a temperature-driven flow of energy. So that's heat, and that's heat flow by convection. And when the water gets to the top, it is in contact with the cooler air. It gives up that energy by conduction to the air, and then the water sinks down. And you can't see it, but in here there are actually patterns of convective motions carrying that heat around. That's the process of convection. This lava lamp is a device that makes use of convective motions. There's a blob of fluid on the bottom, and that fluid is being heated by a heater in here, and as that fluid eventually rises, there it goes. It's beginning to get buoyant enough that it's getting warmer, less dense, and it's rising upward, and then it will rise to the top of the lamp. And there's a beautiful example of convective motion, and then eventually that fluid will cool, and it will sink back down, and the convection will continue. So that's an example of convection. It's the motion of energy, the flow of heat, by the bulk motion of a fluid. Here's a picture of how it works. You typically have a hot surface, a cool surface, fluid rises, cools in contact with the cool surface. It doesn't have to be an actual physical surface. And then the fluid sinks, and it makes these patterns of rising and falling cells of convection. Some examples of convection in your home: you typically have a heater maybe on one side of a room, and the heater sets up a convection pattern, heating air which rises toward the ceiling and then comes back down the other side as it cools and across the floor. And by the way, you end up with a lot of your heat on the ceiling as a result of that, but that's the way a convective cycle is set up in your home. Earth's atmosphere consists of many complicated fluid motion cells that are caused by heating at the equator, where the sun's rays hit most directly, and those cells of convective motion actually transfer energy toward the higher latitudes. If it weren't for those convective motions, the temperature difference between the equator and the poles would be much greater than it is. And another example, inside the Earth, the semi-liquid mantle that the crust of the Earth rides on is heated by heat from below, from radioactive decay primarily, and that heat causes large convective motions, and those convective motions occur very slowly, but they drive the process of continental drift. Convection in the sun carries most of the interior of the sun is dominated by convection as the means of getting energy from the sun's core, where it's generated by thermonuclear fusion, out to the surface where it radiates away. There's a picture of a sunspot and some convective. You see next to the sunspot a lot of little dotted patterns, and those are the tops of rising convective cells that are carrying heat from the interior of the sun to the surface. So this is an important natural process. The last of the three heat transfer mechanisms I want to discuss is radiation. Radiation is the only one of them that works in a vacuum. And radiation, as we'll see when we get to electromagnetism, arises ultimately from accelerated electric charges. And when you have thermal motions, that is high internal energies, high temperatures, you get a lot of thermal agitation, and that gives rise to electromagnetic radiation. So when I say radiation, I'm not talking about nuclear stuff. I'm talking about light. I'm talking about infrared. I'm talking about ultraviolet. And let me give you a quick demonstration here of what I'm talking about. Here is a light bulb. It happens to be an ordinary light bulb, but without the frosting that makes it kind of glow nicely. Instead, you can see the bare filament, and as I turn up the current to that filament with this dimmer, it begins to glow. And at first it glows sort of red, hot, not giving off a whole lot of energy. And as I pass more current through it, it glows brighter and brighter and brighter. In fact, it gets dramatically more bright quite rapidly. And we want to concentrate on that effect right now. Later we'll also concentrate on something else, namely the fact that the color of it is changing. But for now the question is simply how much energy is it radiating, or at what rate is it radiating energy? And that's given by something called the Stefan-Boltzmann law. And I want to look at the equation that describes the Stefan-Boltzmann law. This is a really important law in describing, for example, Earth's climate system. On the left is the power emitted by a hot object through radiation. So there's the power. On the right, there's a quality called the emissivity of the surface of this object. It's a number that ranges from 0 to 1. If the object is completely black, it's 1. If the object is completely shiny, it's 0. In fact, the reason thermos bottles are shiny, here's a thermos bottle, on the inside is because thermos bottles actually have a vacuum which prevents conduction or convection because they can't occur in the absence of material, and the shininess bounces back radiation or makes that E factor called the emissivity very small, about 0, and so we don't get a lot of radiation loss either. That's why thermos bottles are shiny. So let's continue to look at this equation. A is the surface area of the object that's radiating energy. This is a universal constant of nature. It has the value roughly 6 times 10 to the minus 8 watts per square meter per Kelvin to the 4th. And finally, the most important thing here is the temperature in kelvins. It has to be in the absolute units. And it's raised to the 4th power, which is why as I turned that knob, things happened very, very rapidly. The brightness of that bulb went up very rapidly. If I double the absolute temperature, go from, say, 300 kelvins, which is roughly room temperature, to 600 kelvins, the amount of energy goes up by a factor of 2 to the 4th power. That is a factor of 16. So that's a really dramatic effect. And let's take a look at some examples where we actually use this idea. So let me begin by calculating the sun's temperature. Well, that's, I can't just go stick a thermometer in the sun. How am I going to do that? Well, I know what the sun's power output is. It's about 4 times 10 to the 26 watts, 3.9 seconds. The sun is like a 4 times 10 to the 26 watt light bulb. That's about 4 times 10 to the 24 100-watt light bulbs. We know that because we can measure the sun's power at Earth, and we can extrapolate to a sphere as big as Earth's orbit and figure out how much power is coming out of the sun. We know the sun's radius, it's about 7 times 10 to the 10 meters, and the sun has this emissivity factor of about 1. It is almost a perfect absorber and perfect emitter of radiation. So that is a fact we know about the sun. We know this Stefan-Boltzmann law, and I've just set that quantity E to 1, so I've dropped it out of there altogether. The power emitted by the sun is its surface area times this universal constant times the temperature to the 4th. I've told you the power. We know the radius from which we can get the area. What we don't know is the temperature. So let's solve for the temperature. Take the A and the sigma, divide the P by them, and take the 4th root. There we are. The area of a sphere is 4 pi r squared, where r is the radius, so I've got 4 pi times 7 times 10 to the 8 meters, all squared. That comes out 6.2 times 10 to the 18 square meters. Big number, big area, big star. Well, it's actually a relatively small star, but it's a big thing in our solar system. Do the numbers, and the sun's temperature is the 4th root of all that, and I've worked that down to this form because it's actually pretty easy to take the 4th root of 10 to the 16. You just divide the 16 by 4, so it's going to come out with a 10 to the 4th, and the 4th root of 0.11 is about 0.58. It's a bigger thing because you multiply something less than 1 by itself many times, it gets smaller. And so the answer is 0.58 times 10 to the 4 kelvins, or about 5,800 kelvins. Not quite 6,000 kelvins. Remember, not degrees Kelvin, but kelvins. So that's the surface temperature of the sun, about 6,000 kelvins. It's hot. Plenty of things are hotter. The atmosphere of the sun is 2 million kelvins for interesting reasons that I won't go into here. But the sun's surface is pretty hot, 5,800 kelvins. Good number to keep in mind. What happens if I have a system that is receiving energy and also giving out energy? That system, and I don't care whether it's a planet or a house or a human body or whatever, and I don't really care what mechanisms are mediating that energy transfer, but I'm going to discuss particularly radiation in these examples. That system will come into an equilibrium temperature, a fixed temperature, an energy balance temperature, when the rate at which it's getting energy in is equal to the rate of energy going out. If there's too much energy coming in, it'll get hotter. If there's too much energy going out, it will get colder. Let me give you an example of that. So here's a very simple example, a solar heated greenhouse. It's warm in the greenhouse, it's cool outside. When it's in balance, the energy coming in from the sun is coming in at the same rate that the energy that's being lost through the walls of the greenhouse and so forth is going out. So maybe it's conductive losses, it's radiation coming in, it's a mix of these energy transfer mechanisms. And the greenhouse will maintain itself at that fixed temperature because the energy coming in is balanced by the energy going out, even though it's warmer inside and cooler outside. That's when it's in balance. If the greenhouse is too cool for these conditions, because the rate at which something loses energy, the conductive heat loss in this case, remember, is proportional to the temperature difference, the energy out will be smaller than the energy in. The flow out will be less than the flow coming in. Consequently, there's more energy coming in, and consequently, the temperature will go up and the system will come back into balance. What if, on the other hand, the greenhouse is too hot? If it's too hot, because again, the heat loss depends on the temperature difference between the inside and outside, the energy flowing out will be at a greater rate than the energy flowing in, and as a result, the greenhouse will cool down. And so even though it has no thermostat, this greenhouse will naturally come into balance at a particular temperature that's determined by things like the rate at which the energy is coming in from the sun and the thickness of the walls and the kind of insulation and other factors like that. And of course, in reality, night and day and clouds and other things will affect this. But if the sun were steady and the properties of the greenhouse were steady, there would be, and the outside temperature were steady, there would be a fixed temperature determined by this energy balance. So that's how a solar greenhouse works. And a solar greenhouse is just a nice example because it's simple. A far more important example is planet Earth itself, or any other planet for that matter. Because to understand the climate of a planet, to understand its temperature, is most fundamentally, in the most simplest approximation, just to understand this process of energy balance. And we can go a long way, not to the final limit, but a long way to understanding Earth and its temperature, just with this simple idea. So let me give you an example of that. So let's look at Earth's temperature. Let's do it with a real calculation. So here is the picture for Earth. Earth is warmed by incoming sunlight. And it turns out that on average, and this is a rough approximate number, on average, sunlight reaches Earth's surface at the rate of about 240 watts for every square meter of Earth's surface. Now, there's less near the poles, there's more near the equator, there's issues of night and day, and that number averages that all out. About 1,000 watts on a square meter in direct sunlight, but it comes out, not surprisingly, to something like a quarter of that. That's the rate at which sunlight is coming in to warm the Earth. Now, the Earth gets warmer. The Earth can't lose energy from its whole self by conduction. It can't lose energy by convection. Although both those mechanisms can function internally, particularly between the surface and the atmosphere, the ocean and the atmospheres and things like that. So they become important in the more detailed look at climate. But the big picture is the only way the planet can lose energy to space, because space is a vacuum, is through radiation. And it turns out at the Earth's temperature, which is about 300 kelvins, most of the radiation is invisible infrared. So here's the outgoing radiation, and that outgoing radiation is established by this Stefan-Boltzmann law that we've been talking about. And it depends on Earth's temperature. The warmer Earth is, the greater the rate of outgoing infrared. And so what has to happen for Earth to come into energy balance is the outgoing infrared has to equal the incoming sunlight. That's the condition for energy balance on planet Earth. So we write the Stefan-Boltzmann law. Earth turns out to be an object with emissivity approximately equal to 1. So again, I'm going to write P equals A sigma T to the fourth. Now, I haven't given you the total power coming to Earth from the sun. I could have, but I gave you the average power per square meter of surface. So I'm simply going to divide this equation through by A to get the power per area. And the power per area is this universal constant times the temperature to the fourth power. In energy balance, that quantity, P over A, the power per unit area emitted in infrared radiation, had better balance the power per unit area coming in sunlight. So P over A, sigma T to the fourth, that is, has to be 240 watts per square meter if the planet is to be in energy balance. Let's solve for the temperature. So what am I going to do? I'm going to take sigma T to the fourth, I'm going to equate it to 240 watts per square meter, I'm going to divide through by the sigma. That's going to give me 240 watts per square meter divided by that sigma, and that gives me T to the fourth, so I've got to take the fourth root. Let's work that all through. I'm just doing arithmetic here. I end up with 42 times 10 to the 8 kelvins. And again, I did it so I got a nice multiple of 4 on that exponent rather than putting a 4.2 or something else there. And 4.2 times 10 to the 9, I made it 42 times 10 to the 8th, because the fourth root of 10 to the 8th is 10 squared, and the fourth root of 42 is about 2.5 or so. And so if I work through that, the answer is 255 kelvins. If you work that out, that's about 18 degrees Celsius below zero. It's about 0 degrees Fahrenheit for the average temperature of the planet. Now, that's not bad. That's, within the right ballpark. It could have come out 1,000 kelvins and the Earth would have had its oceans boiled away. It could have come out minus 100 Celsius and the Earth would have its oceans frozen solid. So this is in the right ballpark. But it does seem awfully cold for the average temperature of the Earth. I mean, here we are in January right now in mid-latitude near Washington, D.C., and the temperature outside is just about freezing, which is 0 degrees Celsius, 32 degrees Fahrenheit. And I could easily imagine that that's below the average temperature of the planet when you think about the tropics and all. So something else is going on here. This doesn't tell us the whole picture, but it tells us the biggest part of the picture of what Earth's temperature should be is right here. I'll give you just a little hint about what's causing the rest. The rest is caused by the greenhouse effect and the absorption of outgoing infrared by carbon dioxide in the atmosphere, and that's a whole different story and why Earth's climate is in fact right now changing. But here is the bottom line basic physics, the basic thermodynamics of how you establish planetary temperatures, including Earth's. Okay, well, let's wrap up with a summary of what we've learned here in this lecture on heat transfer mechanisms. We've learned that there are 3 major heat transfer mechanisms: conduction by direct contact, molecular collisions doing the transfer, convection by the transfer of energy through the bulk motion of a fluid. There is natural convection. I didn't go into it, but there's also forced convection where you use fans and things to move the air around. But the natural convection, gravity and density differences give rise to it. And then there's radiation, transfer by electromagnetic radiation, the only mechanism that works in vacuum. And finally, we looked at the process of thermal energy balance involving radiation and other transfer mechanisms, and we get a constant temperature only when the rate of energy going in is equal to the rate coming out. Well, you can stop there, but let me give you a challenge if you're interested. Let's do a more realistic house. So in that heating a house example, let's give this house 10 double-glazed R2 windows. Modest windows, not very good, and they're each 2 feet by 4 feet. Now what's the daily oil consumption? Well, the total window area is 80 square feet. There's the window heat loss calculated with that 1/2 BTU per hour per square foot times the 80 square feet times the 60-degree difference. The wall area is almost what it was before, but a little bit less, so the wall heat loss goes down a little bit. The ceiling heat loss is unchanged. Add them all up, you get 192,000 BTUs per day. That takes the oil consumption up from 1.5 gallons to 1.9 gallons per day. So that's a more realistic look at this house.